We've come to our last lesson in the counting unit, and this lesson is called Assignment Problems, Balls in Bins. Now, right at the end of the last lesson, we did have an example of a problem where we had a certain number of balls and certain number of bins, and we needed to distribute them. That was under certain situations, but as you can see by this chart here, we have all kinds of possibilities. So over on the left, you see there's two rows that are labeled. One is indistinguishable balls and others as distinguishable ones. So we have different scenarios for that. And then but across the top, we have maybe there's some kind of restrictions for the number of balls in a bin. And so the first column is headed no restrictions. The second one is at most one ball per bin. And the third column is the same number of balls in each bin. Okay, so as you can see, there are a lot of categories. And because there are so many categories, I just figure that you have enough categories to be trying to remember from the previous lessons. So I just wanted to let you know that on any problem that I give you on the test, that will be that where you can use one of these formulas, I will say this is a balls in bins problem. So that way, and then I'll also actually let you see this chart. So you can look at the chart and then figure out which category it's in. So, so that's just one less, or 6 less categories that you have to worry about identifying on your own. So basically, well, you would have to identify one out of these 6, but when I say this is a balls and bins problem, at least you know that you're limited to these, and you don't have to get those mixed up with all of the other types of problems we've done. So anyway, today in this lesson, we're going to go over each of these possibilities and actually see how we could come up with all of these ourselves if we just would think about these situations in the right way. So we're going to look at all of them and see how these formulas have come about. So first of all, let's look at n indistinguishable balls into m distinguishable bins. Let me say one thing about the bins before we get started here. In all of these cases, all 6 of these categories within this table, we're always distinguishing the bins. We're saying there's going to be a, maybe we would label it a bin number 1 and a bin number 2, or maybe we just have a purple bin and a green bin, but we're always going to say that these bins are distinguishable. So if I would just, like in this case here, I've just changed the number of balls in bin 1 and 2, I've just switched them, we would still consider those different placements because we're going to consider the bins themselves distinguishable. Okay, so this first example is, you can see I've circled the no restrictions at the top in this table, and I've also circled the indistinguishable balls. So that means they're not labeled, they all look alike. Okay, well, hopefully this formula looks familiar to you because this was the category that we talked about in the last lesson. It turned out to be a situation very similar, well, that was bijection for the counting the multi-sets, where we're choosing a certain number of cookies from a certain number of varieties and that kind of thing. And so this is the formula here, that n plus m minus 1, choose m minus 1. That's the formula that we saw last time and that we use in several different situations. So anyway, let's kind of think through this again so we can come up with this formula here. So think about the bijection that we could have between the placement of balls into the bins and the number of ways to select 12 objects from 4 varieties. Because, as I said in the last time, think about, in this case here, there were those pictures. Imagine those balls just being like maybe tickets for buying a cookie. And you would then hand over a certain number of tickets for the first variety of cookies and a certain other number of tickets for the second variety, and so on. And so you see that we could have a bijection between those two, placement of the balls in the bins and just actually choosing different varieties of cookies. So since we do have a bijection, then we know that we can the same number would apply whether we're looking at one of those, the placement of balls, or the selecting certain objects. So that's why we can use this formula. So here's this fact: the number of ways to place n indistinguishable balls into m distinguishable bins is the n plus m minus 1, choose m minus 1. And this bijection that is brought up, it's not real obvious how we come up with that formula. But if you remember when we talked in the last lesson, we would take these scenarios like this and make a bijection from them to this code word where it had zeros for our selections of the different varieties and then ones to separate the varieties. And that's how we officially and at the beginning came up with this formula. So this is one, again, that if you would remember that you can, you would have a bijection to the code word, you could think it through by thinking of those code words, and you would come up with this formula. But again, if I give you a problem on the test and say it's a balls and bins problem, then you already have all of these that you would look at and try to distinguish which of these 6 it would be. But in this case, n indistinguishable balls into m distinguishable bins. No restrictions. Okay, let's go on to a new one. We have no restrictions again, but now you see that distinguishable balls is circled. So now we've got balls that might be either numbered or have letters on them or some way are all unique in some way. So in this case here's a picture where we have 3 balls in both bins 1 and bin 2 in both scenarios, but we would consider it differently because consider it a different placement, because on the left we have balls 2, 3, and 7 in bin 1, and on the right we have balls 2, 3, and 5 in bin 1. So you see that those would be considered different now because we have these distinguishable balls. So let's think it through. We just have to look at it a certain way and use what we've learned already and come up with what that it looks like we're going to get m to the nth, but let's see how we might do that. Well, let's think about it this way. Think about, we have all of these balls, let's say they're numbered from 1 up to n. Now let's think about this. Let's think about each ball and thinking how many choices we have for the bins that we're going to put that ball number 1 in first. So we'd say, well, we're saying here in this picture there's 4 bins, but we're saying in general we're going to say that there's n balls that we're putting into m bins. Okay, so how many choices would we have for that ball number 1? We would have m choices. We could put ball number 1 in the first one or the second one, and since there's m of them, that's how many choices we would have. Now, since there's no restrictions, when we would come to ball number 2, we don't have to say, well, I can't put it where I've already put ball number 1 because there's no restrictions. I could put all of the balls in the same bin, so I can just it's just independent of what I did for the first ball, and so I could again think to myself, How many choices do I have for ball number 2? How many different bins could I put it in? And again, we would have M choices. So we would have M choices for ball number 2, and we would have M choices for all of the balls. So now we could use the product rule. Remember we said, if we're talking about a certain number of choices, we could actually say how many choices for each of these different parts of, events, or sequences that we would have. We could look at our sequence as, let's choose which bin for ball number 1, and then choose which bin for ball number 2, and so on. So we have a sequence of events, and so the product rule would say that we would just take the number of choices for each of those events and multiply them together. So we would have M times itself, and we would do that n times. So it would be M to the nth. So we would say then there are M choices of bins in which to place each ball. So by the product rule, then it would be M times N times M over and over and over, which would be then M to the nth. So that gives us this formula up here in that table bottom left. That's how we get that. And again, you won't have to come up with these for the test. You'll have the table. But I do just want you to see how really easy it is to come up with all of these if we look at the situation in a certain way. Okay, let's look at this next one. So we have indistinguishable balls, so they all look the same, but we have at most one ball per bin. So here's a picture of 5 bins, and some of the bins have one ball, some of the bins have no balls, because it says at most one per bin. So we're going to have, these are the only possibilities, either have no balls in there or have one ball in there. So if you look right below that, that black circular circle up there that says at most one ball per bin, underneath it says M must be at least size N. So we've got to have more bins available than there are balls if we're going to have this situation, right? Well, at least we have to have at least the same number or more bins, right? Because if it's the same number, then we'll just put one ball in each bin. But if there's more bins for the balls than the balls, then we'll have some bins that are empty. But if we would have more balls than there are bins, then we couldn't do it, because we would have to place more than one ball at least in some of the bins, and we're not supposed to do that in this scenario. Okay, so we're just assuming then that there's more bins than there are, or at least as many bins as there are balls, and we're assuming, as you see, we're on that top line of the table, which means that we are considering indistinguishable balls, so they aren't numbered. Okay, so let's think how we can think this through. So each bin is either going to have 1 or 0 balls. So when we do a specific placement, we could look at this as indicating which subset of the bins get a ball. So for instance, this picture here, we'd say that there's 5 bins, and I've chosen 2, 4, and 5 to be the ones where I put those balls, right? So if you think about it, it's going to be an M choose N situation. We've got M bins, and I need to choose N of them in which to put the balls, one ball each. So the number of different placements of N balls into M bins with at most one ball per bin is equal to the number of subsets in the M bins, which is the M choose N. Okay, so that gives us that formula up there. Now let's go to distinguishable balls. So they are numbered or somehow distinguishable from each other. And then at most one ball per bin. So here you have a picture of 5 bins, only 3 balls, but they are numbered. So let's see if we can figure out how we might come to the conclusion of what they have up there in the table. Let's think about it this way. We've got, the numbered balls, in this case, just 3 of them. So one is numbered 1, one is 2, one is 3. And if we ask ourselves, which bin are we going to put number 1 in, ball 1 in? Which bin are we going to put 2 in? Which bin are we going to put 3 in? We could just write that number underneath. So in this particular picture, I have ball 1 in bin 4, and ball 2 in bin 5, and ball 3 in bin 2. Well, if you think about it then, since especially, and because we can't just go putting, we're not going to be able to say, I'm also going to put, if I had a 4th ball, I'm not going to be able to put it in any of those bins that already has 1, right? Because we can only put at most 1 ball per bin. So we can think about it as lining up the bin numbers under the numbered balls, right? So I have those numbered balls at the top, and then I'm just lining up the numbers, the bin numbers, and they can only appear once. They can't, because we can't have more than 1 ball in a bin, so they can only be there once. So only n bins will be used out of the possible m bins, right? Because remember that n is going to be either the same or smaller than m. And, it's only how many balls we have where we do this, and so that would be n of them. So only n bins are going to be used out of a possible m bins. So it's just like saying, let's take all of the numbers related to these bins and line them up in a certain order, but only taking n at a time. So see, in this case here, we only needed to take 3 at a time because there were only 3 balls. So it was like taking the numbers 1 through 5 and choosing 3 of those to line up in a certain way. And what that is a permutation of m things taken n at a time. With this picture, it's 5 things taken 3 at a time. So that's how we get that permutation, m things n at a time. Okay, now we've got indistinguishable balls, so we're back to having them all look alike, but now we're over into the right column, and this says we need to have the same number of balls in each bin. Okay, so and look underneath that at the top right of that table, it says m must evenly divide n, right? So like here I have 5 bins. I can't have 8 balls and still get the same number of balls in each bin, because I'd have some balls left over. I'd have to cut them up so that I can get them evenly distributed, and we're not going to do that. So that's why m is going to have to be must evenly divide n. So yeah, m must evenly divide n. Yeah, so in this case here, remember n is the number of balls there are, and it looks like we have 10 of them there and only 5 bins. So 5 is what m is, and 10 is what n is. So it's true that 5 does evenly divide 10. So it'd be something like this. Okay, so let's think about this here. Let's just look at this case here where we've got 10 balls and we have to put the same number in each bin. Well, that would just mean there's 2 balls in each bin. And since these are indistinguishable balls, then that's only one placement. There's no other way to place those balls other than 2 in a bin. So since the number of balls in each bin is determined and the balls are all identical, there's nothing to decide about the placement. So there's going to only be one way to place those balls. So that's how we get this 1 up here in the table. Okay, last category, where we've got n distinguishable balls, so they're back to distinguishable. We can consider them as being numbered into m bins, and again, it's always distinguishable bins on all of these. We're just assuming the bins are always distinguishable. But here we have, you look down, look up at that table, and at the very top right it says same number of balls in each bin. So that's just kind of the same situation as we just talked about. However, the difference is now we have the distinguishable balls, which are numbered balls. Okay, so let's see if we can figure this one out. If you take a look at the formula in there, it looks a little bit more complicated, so it looks like maybe it would be hard to figure out. But I think we'll be able to figure it out, at least for like just this fixed example here, where we have only 5 bins and 10 balls. We'll see if we can figure it out. So let's say that we do have 10 balls and 5 bins. Well, think about this. I know that only 2 balls are going to be allowed in each bin because we have to have the same number of balls in the bin. So let's start by choosing which balls we are going to put in bin 1. Well, there's 10 balls to choose from, and I'm going to choose 2. So I'd have 10 choose 2. And again, we can look at this as a sequence of events and then multiply the number of ways that we, the number of ways that we can do each of these. So again, we're going to end up multiplying them together because we're using the product rule. So that's why you see all of these multiplied together. But each of these right here at the on this when we say 10 choose 2, 8 choose 2, those are corresponding to each of the bins. So the first one corresponds to the first bin. We had 10 to choose from, and we chose 2 to put in bin 1. Now we go to bin 2, and we've already placed some balls into bin 1. So there's only 8 balls left, and we could say that I have, out of 8 balls, I need to choose 2 of them to go into bin 2. And then the third one is now I only have 6 balls left by the time I get to bin 3, 6 things 2 at a time. Then only 4 left when I get to bin 4, so 4 things 2 at a time. And then bin 5, 2 things 2 at a time. Now, if I were to use the formulas for these combinations here, you don't necessarily see it here, and I guess I didn't show how it comes about. But it turns out that with all of the different kinds of canceling that we do and everything, it turns out that we end up getting just the first number of balls at the top with a factorial on it, so 10 factorial in this case, divided by, and then we're going to have however many balls in the bins times, factorial, taken the number of times of however many bins there are. So here we have 2 factorial in there 5 times. So 10 factorial comes from the 10 was the n number of balls, and the 2 down below was how many balls in a bin, and what was that? That was n divided by m. That told us how many balls in each bin, and that was 2 in this case. And how many times do we have 2 factorial? Here we have 5 factorial, and that correlates to the number of bins we had. So now let's look at this formula down here, over here at the very bottom that came up. This shows just in general what it looks like. But if you just kind of take a look at the bottom, the very far right, at least let's just compare that to what we got with this 10 balls with 5 bins. We did have the n factorial on the top, And then the 2 factorial was the n divided by m, how many in a bin, and then factorial, and we multiplied that together as many times as we have bins, so it would be taken to the mth power. So again, here on this bottom line down here at the bottom of the slide, I didn't really show you how we got that. Again, though, you would use the formula and then cancel a bunch of things out, and it ends up being this all the time. Anyway, so even though this formula up here in this last formula in the table looks pretty complicated, I hope you can see how it was fairly easy to come up with for our little example of 10 balls in 5 bins, and then hopefully you see how we can generalize it and then take my word for it that it simplifies as I'm saying it does here, and then we end up getting this formula here. So you might think, okay, this is not bad. You'll tell me how many balls there are, how many bins, and if there's restrictions or whatever, and then I'll just go to the table and use the right formula. That is true. However, it turns out that there are other problems that are not given to us in terms of balls and bins. We might have other things. We're not talking about balls and we're not talking about bins, and yet it can be equivalent to a balls and bins problem. So that's why I'm telling you that on the test, when it comes to doing any of these problems, even though the problem doesn't even talk about balls and bins, if it's one that translates to a balls and bins problem, then I'm going to tell you that it's a balls and bins problem. So then you kind of have a clue that, oh yeah, I'm going to look at this table, and I will give you this table on that problem that I say is a balls and bins problem, so you'll have it there to look at. Okay? But it won't necessarily be talking about balls and bins. So here's an example. 10 identical coupons will be given out to 20 different shoppers in a store. There's a limit of at most 1 coupon per shopper. How many ways are there to distribute the coupons? So we could look at this as the shoppers being the bins, right? And the coupons being the identical balls, because all those, just imagine all those different shoppers waiting around to be handed a coupon. Some get them, some don't, and it says there's a limit of at most 1 coupon per customer. So we would look over here and I would tell you, by the way, this is a balls and bins problem, and so you'd say, well, okay, I've got I know I could find what N is, I could find what M is. There is a limit of at most 1 coupon per shopper, at most 1. So we see that we use this middle column where it says at most 1. But then we have to decide, do we have indistinguishable balls or distinguishable ones? Well, here we're talking about coupons and we're told they're identical. So therefore it would be the bottom line. So it would be middle column, bottom line, which would, I'm sorry. I think I might have said distinguishable. I don't even remember. So sorry if I did say that. I was looking already down here, but no, this is definitely at most 1 and a indistinguishable. The coupons are indistinguishable. So it would be this one here, the M choose N. So hopefully you see how we would come up with that. Now, if those coupons had been different, like one was for $1 off of peanut butter and another one was, half price for a loaf of bread or something like that, and they were all different, that's when we would have come down to the middle column bottom line. But no, we're at the middle column top line since the coupons are all identical. And we could come up with what N and M is and then just put it into the formula, right? N is like how many balls we have, and then the shoppers are the bins. Okay, let's look at this one. 10 identical coupons still will be given out to 20 different shoppers. There is no limit on the number of coupons that can be given to a customer. How many ways are there to distribute the coupons? Okay, so now there's no limit. So now we would be up here because we still have the indistinguishable balls, or in this case, identical coupons. And there's no restrictions. So we would use this one, the one in the top left white box in the table. And again, we would see that the number for N would be how many balls that are now coupons, so that would be 10. And then the bins would be number of bins 20 because it's 20 shoppers. Here's another example. 8 different tasks are assigned to 20 employees at a company. There's no limit to the number of different tasks that can be given to any particular employee. How many ways are there to make the assignments? And again, if I gave you one like this, I would say, and by the way, this is a balls and bins problem. So again, we can look at the people as the bins, and that we're going to be doling out tasks to the people. So it's like we're putting, we're handing out, maybe we have a Post-it note for each task, and we're handing that to an employee for each task, and it says there's no limit, so we could choose one employee to give all of the tasks to if we really wanted to. Okay, but the key part here is that they are different tasks. So one might be, vacuuming, and another one might be, cleaning the kitchen sink. So anyway, they're completely different. Okay, so we would go over to the table and say, well, we've got, this is a balls and bins problem, but the balls would be distinguishable. They are different. So we would come down to the bottom line, and there's no restrictions, so that would be this one right here, M to the N. And we do know what N and M are, right? N would be how many things are being distributed, so that would be 8, and then 20 would be the number of bins, which we would be calling our employees. That's what our employees would be. Okay, so now we've done 3 of these. Let's do 3 more examples so we see those other ones that we haven't used yet. So we've got 8 different tasks. They're assigned to 20 employees at a company. Each person can be assigned at most 1 task. How many ways are there to make the assignments? Okay, so again, we're on the line for distinguishable balls because the tasks are different. But we do have at most 1 task, so we would be on the middle column where it says at most 1 ball per bin, because at most 1 task can be given to 1 employee. So it would be this one here, right? It would be the permutation of M things N at a time, because we've got the distinguishable balls and at most 1 ball per bin. And we would know what N is and M is, so we could put it in there and find the answer. Okay, here we've got 15 identical chocolate bars, and they're given out to 5 kids so that each kid gets the same number of chocolate bars. How many ways are there to hand out the chocolate bars to the kids? Okay, so notice that, and we could again look at the people, these kids, as the bins, and we've got these identical chocolate bars that we're going to distribute. Each kid gets the same number. So if there's 5 kids and we need to distribute 15 chocolate bars, we'll give 3 to each kid, right? So so we would know that that would be how many. How many ways are there to hand out the chocolate bars? So as far as the balls go, we would have to say it's indistinguishable because the chocolate bars are the same. So it would be on the first line of this table. But we'd have to have the same number of chocolate bars per kid, so that would be equivalent to same number of balls in each bin. So that would get us over here, and we see that, yeah, is what we would think. There's only one way to do that, and that's give 3 chocolate bars to each kid. Now, a grandfather's giving away all 45 coins in his coin collection to his 9 grandchildren. The coins are all different, and he wants to give the same number of coins to each grandchild. How many different ways are there for him to distribute his collection? So the grandchildren would be the bins, and the coins would be the balls. These coins are different. It says the coins are all different. So we would be on the bottom line of distinguishable balls, and we want all of the children to have the same number. So we'd be over on the right column. So that would be this one here. And notice we could do this with the 45 coins. We can distribute that equally to 9 grandchildren. So that would work. Okay, so we've seen now 6 examples that didn't even mention balls and bins, but yet those would be problems where we can use these formulas. So anyway, just kind of practice that and just know that if I don't say this is a balls and bins problem on your test, then you're not going to be using this table, and you don't have to worry about that. You're going to be thinking through all of those other categories that we've already talked about. Okay, and there will be, I believe, only one problem that uses that is a balls and bins problem, and so you'll have to figure out, which of these formulas to use for it. Now there's a few additional exercises you can do for practice. So the first exercise is good. The third exercise is good. So you can do those, and I will open up the solution so you'll be able to see the solutions for that. And of course there are some participation problems, and I can't remember which of the sections for this week had the challenge exercise. I think there's only one challenge exercise, so it might be from this section. I'm not sure, but if so, then you would do the challenge also. And I've said this a lot of times already, but I'm just saying this so that I can reassure you, because I know we already had a lot of different categories, and then all of a sudden I throw in the last lesson basically 6 more categories, although really one of them we had talked about last time. So let's just say 5 new categories I threw at you. That's why I want you to know that I will identify that so that you don't have to worry for every single problem you're reading on the test. Is this a balls and bins problem? And try to figure out which one it is. I won't do that to you. So there'll only be one, and I will identify it as balls and bins. I wanted to point out that I have a study guide that is posted on Canvas, and I think it'll be really helpful for you, because the challenge is going to be being able to read a problem that I give you on the test and be able to think about, well, what section did we talk about that in, and therefore how would I answer this, right? So there are different categories, and so what I wanted to do is give you a study guide that just gave you just a bunch of problems, and then that would give you a chance to practice answering all these questions, not knowing which section they came from. Okay, so you can click on the study guide for counting test and get a copy of that, and even print it out if you want, or just keep it on your screen, but I think you really definitely want to practice with that before the test comes. And I wanted to give you this last lesson and this study guide early enough so that you'll have plenty of time to spend on studying for this. So this is what you would get when you click on that study guide. You get something that looks like this. There's actually 35 questions on there. So a lot of questions are there. Now these questions are straight out of the lectures. Okay, so it's the problems that I did in class. So the reason I did that is because the answers and the solutions are easily available because they're within our notes, and you can even go to the video, the corresponding video, and see me explain the whole thing. Now you do see there that it says right after study guide there, when you clicked on study guide, right underneath it says counting, I think something, counting problem solutions PDF. So if you will be able to see the answers, because on the end of this study guide there are the answers there. So you'll be able to check your answers, but if you don't get the same answer as I have listed here, then you can go to that PDF that's listed right under the study guide and see it worked out. And even I think I might have even said something like what section is from or something, so you can go and look. I might not have on that, I'm not sure. But anyway, definitely spend a lot of good time on that. Now something else though that I think will be very helpful is these what are called Quizlets. I used this website called Quizlet and made some flashcard activities that you can do. For one thing, of course, you need to be able to take all of these problems and get the actual answer. But I thought it would be good practice to also just go through all of these questions and just tell yourself, or practice coming up with what category it's in, and so how you would get the answer. Like you might read a problem and say, oh, I know, I would use the product rule on that. Or, oh, I'd use the product rule, but I'd have to find the complement and then do a subtraction using that complement rule thing that we learned, that kind of thing. So what I've done is I have two Quizlet flashcard activities. One is for testing you to see if you know what type these problems are, and that's under problem types, and that would be this first link. But then I've also got another one where you are given the problem, and then you'll find out what the answer is. So what these look like is they're flashcards. So let's say you click on this problem types link, then you would get something like this. Quizlet comes up. That's the website. Now be sure and click on shuffle, because if you don't click on shuffle, they'll come in the same order they are on the study guide. Now the reason why you might not want that is I think I did, when I created the study guide, pretty much put them in the order that we learned them. So like the earlier ones are all using the product rule, but in this activity where you're going to just be wanting to look at a problem and then just try to figure out which type of problem it is, so you know how to answer it, you'd want these shuffled so that they come in different orders. So click on that shuffle so it's highlighted, and then you'll see a problem here. This one says how many serial numbers of length 12 are possible with at least one 5. So you would think, what would I use for that? What category was it in? And then you could guess, and then to see if you're right, you click on this little flashcard. Kind of look at it as this is one side of the flashcard, and when you click on it, then it's going to show you the other side that tells you the answer. So if you clicked on it, and let me say this before I go on, you have to be careful when you click on these questions, because if you click on the actual text, like if I clicked and happened to be in this text area here, then the computer, the website thinks that you want the problem read to you. So somebody will start talking and reading this aloud. And that's probably not what you want. If you want that, sure, you can go ahead and do that. But if you're just trying to click on it so that you can see the other side of the flashcard to know what the correct answer would be, just be sure and click somewhere not exactly on the text, down in the bottom empty spaces here. Okay, so so you would think, what category is that? Come up with what you think it is, and then click on it, and then it'll turn over and tell you, well, this one you'd use the product rule, but you're also using the complement rule there too. That's kind of how you can work with those. So as I said, there's two different activities. One just to help you be able to categorize all of these questions, and the other one to actually give you a problem, and then you have your paper and pencil and you try to come up with the right answer, and then click on it and see if you got the right answer too. And all of these questions on those flashcards are the very same questions on the study guide. Okay, so I would suggest spending a good amount of time studying for this test so that you can be really, have a lot of practice so that you are able to look at a problem. I'm not going to, like if, let's say, that permutation with where we had to glue two objects together. We had an example of the bride and groom in taking wedding photos. And I think I have that problem in the study guide. So just know that you don't want to, as you're studying, say, oh yeah, the bride and groom problem, I always know that's gluing two together and it's a permutation. You don't want to do that because the problem I give you on the test won't be talking about a bride and groom. It'll be a different scenario. So instead you want to think, oh yeah, this is an example of where we're lining things up in a certain order and there's two objects glued together. Okay, so don't be just getting whatever the problem's about. If it's about donuts or cupcakes or whatever, don't get that, don't try to memorize what category it would be based on what items I have in the questions, because again, the questions that I give you on the test will be about completely different things. Okay, well, good luck. Let me know if you have questions. If you don't understand something, send me an email. We can meet on Zoom if you'd like, and just look on Canvas to see when that test is. I am posting this video early so that you will have a chance to finish this unit up and then have some extra time to study if you'd like. Okay, good luck. And after the test, we'll go on to one more unit before the end of the semester.